record on this. Okay, now in this section, we are in chapter 9 now. Chapter 9, we will be exposed to a very different avenue. Oh, sorry, I opened the wrong one. Completely different avenue, because this is where that tricky part start from in the statistics. Chapter 9. But don't worry, we can get through this one easily, because I'll explain everything from the scratch. In that way, you guys get like a very clear picture what's going on. See, chapter 9. Okay, the distribution of estimates. We had estimates earlier. So now estimates, where the estimates are coming from? Why they're going to talk about the estimates? When they talk about the estimates, before that one little bit, we can go back to the beginning and have a look at it and see that what's going on over here. So in statistics or data analytics, okay, in the parametric framework, mainly there's a procedure called the statistical inference. See? Inference, okay. Statistical inference, mainly two parts. One is estimation. The other one is testing. Now you might be thinking that who will be estimated, who will be tested? Who you're going to test? Parameters. Who will be estimated? Parameters, such as population mean, which is denoted by mu, population standard deviation, which is denoted by sigma. Okay, those are the main two things, and etc. Okay. See? So those are the one we are trying to estimate. Parameters such as population mean, population standard deviation, try to be estimated. Not only that, I can add some more. Okay, I can add more. Be a beta note. See, since we have already done beta note, we can talk about that one too. We can say population intercept, which is beta naught, population slope, which is beta 1, population error is epsilon, all these, etc. Like that. Okay, those are to be estimated. These cannot be computed because they were unknown. These all are unknown. See, unknown. You don't know about them. Unknown and fixed. Fixed means you have only one value. One value, or we can say unique. See, one value. Unique. Testing again, who will be tested? Parameters. Again, parameters. Parameters will be tested. See, parameters will be tested. Like for instance, if I write it's an example H naught, I can test population. See, population average. Certain value. Say, let's say population average is equals to 150 versus its counterpart mu. This alternative hypothesis, we're going to do that one in large scale later on, more than 150. See, somebody going to claim and say that on average that the cops going to that fine for people who are speeding $150. Then we're going to check that whether this is true or not. Then you will be entrusted with that task and see whether this is true. This is the claim. We say that they are charging more than $150 for their fines. If that's true or not will be claimed. That claim will be tested against counterpart. Counterpart means null hypothesis. It's an alternative hypothesis. We're going to come to that one in detail, but I'm just saying this one now. Hypothesis. This one, alternative. You have to order them, give the alternative along with the Now, see, something like that. If you want to test, you have a data mechanism. We have mechanism you can do manually, and you can use in the R program or SAS or Python or any program. You can get this done. Okay, and pretty much again here, this estimation I can do into branch out into two parts: point estimation and interval estimation. We're going to talk about pretty much everything in this class. Like we're going to touch on the surface. Okay, point estimate. What that means? Point estimate means, like I would say, point estimate of population. The population mean mu is the sample mean, like that mean, which is y bar. See, point estimate of population mean mu is the sample mean y bar. See, y bar. If I write like this one here, see, you can say what is the estimate. Estimate means hat is would estimate y bar. See, instead of going to that population mean, you can think about an estimate for that one. If you want to know the average height of all national university student, you cannot access to the all university student. There's it's a time, it's a wasting, it's a time wasting and money wasting and then labor wasting, like that. So in that way, we're going to go ahead and pick up the sample. Based on the sample, you're going to just calculate the sample mean. It's enough. See, based on a sample, you pick this one. Okay. So instead of that one, the point only one, the practitioners, they say, they feel like, no, we are not happy with only one estimate. I need to give me a branch, sorry, give me an interval of estimates, interval of points estimate. That's called the confidence interval. See, under this one, confidence interval, we're going to talk about that one in chapter 10, confidence interval. Confidence interval, CI. CI, confidence interval. Whose confidence interval? Mu's confidence. CI subscript mu. I'm gonna write confidence interval as a kind of like an interval. Confidence interval means interval. I'm gonna start from one corner to the other corner. See, I'm gonna say this corner, I have a lower bound, LB, to upper bound. See, like that. You will see down the road that one. See, lower bound to upper bound. See, I'm gonna write rest on this side, where lower bound is nothing but point estimate minus standard error. Sorry, margin of error. Sorry, margin of error. Margin of error. Margin of error is nothing but the maximum error that can incur by estimating that unknown parameter. See, maximum error, max error incurred in estimating the parameter, whatever the parameter you have. See, margin of error, normally we write MOE. See, MOE, margin of error, MOE. So if you add to this one too, let's say that for mu, if you write to this one for mu, a lower bound of mu is nothing but y bar plus sorry, y bar minus, okay, minus margin of error. See, margin of error. And similar fashion, you can write the upper bound too. Upper bound, I'm going to write over here. Upper bound is nothing but here, this means lower bound. Lower bound. This one upper bound. Or upper limit. Point estimate. Plus this time margin of error. See? So then if you write this one, upper bound of mu, if you write y bar plus margin of error. Yeah, again, I can write margin of error is nothing but critical value times standard error. Standard error of the estimate. What that means, I'm gonna write one more, right? There's a critical value times, that means standard deviation of the estimate. That's the part we are trying to talk about today. Okay? Standard deviation of the estimate. Okay? I'm gonna write margin of error, critical value, I'm gonna write with the aid of Z. ZC, see, from the standard normal distribution. I'm gonna get that one from standard normal distribution. Cutoff value, sometimes we call the critical value, cutoff value, table value, see, critical value, that's other name, see, cutoff value, table value, because it has been taken from a table, see, table value, another name, CC times standard deviation of, see, standard deviation of y bar. This is the one that we are seeing. Look at how I write. Standard deviation is denoted by sigma. See, this is nothing but standard deviation of y bar. See, y bar. See, standard deviation of y bar. So that means, see, therefore, see, I'm going to write this way. Lower bound of mu, I'm going to write y bar minus cc, okay, cc sigma y bar, see, sigma y bar. I can write this one, go further down, and I can write this one another way too. See, it is nothing but sigma over square root 10. Sigma is nothing but population standard deviation over square root of sample size. See? So you go to y bar, this is very tricky part. Y bar, we have only one y bar, one sample mean only. Why? How come that you have a spread? In order to talk about spread, you have to talk about the histogram. Yes, that's what we are planning to do today. So this is same as, look at how I write. Y bar minus CC sigma over square root 10. See? When you run that this confidence interval and everything, that you can easily get this one. But I'm focusing on this part today. This part today, which is completely related to the next the topic. Then again, since we don't have sigma y bar, look at what I'm gonna do. I'm gonna replace that one with its hat over square root 10. Hence, sigma is unknown. It will be replaced by its own estimate. Then y bar minus CC, nothing but S, see, sample standard deviation. I can use the sample standard deviation, see, sample, instead of population standard deviation, can I use the sample standard deviation? Yes, see, here the mu. Similarly, upper bound of mu you can write in a similar fashion, y bar plus CC S over square root 10. This is the part we tackle today. This is the part we tackle today. See this part. And this part as well too. See, it's the point testing. See, that's nothing but the point testing. Point testing. Point testing. Point estimate is y bar. Margin of error I split into two parts. The maximum error that can incur when you in the that in any that electronics, electrical law, chemical law, mechanical that components that manufacturing that they're gonna keep that this margin of error to up to certain point, see, up to certain value. We cannot exceed more than that one. Then we're not gonna send that one to the for the sale outside. We're gonna keep in their warehouses for a long period of time, certain period of time, see whether they're gonna have some kind of that defects or anything like that. Then they're gonna send to that. That's called the bathtub shape, like a keep in this one. Then they're gonna send to that some stores for them to be sold out. See, in that period, and then wearing off. In the wearing off, they're gonna go ahead and manufacture another the batch of those items. So in order to, they're not going to send it to the market right away. They keep in their warehouses and see whether they're going to break down or anything like that. It's called the, see, infants that time period, then regular time period and decaying. It's called the bathtub shape. That's a different area for the talk about the reliability, but even for that one, these are connected. But anyhow, that here, that's what we mainly doing. See, so if you go back to this one again, see, we are on the estimation and testing. Testing, we come to that one later on. See, we can talk about that one later on. See, testing. We have this one. See, and under that one, we have a two setting: point estimate and interval estimate. See, interval estimate. And then we're gonna write this one as like an interval, lower bound and upper bound. See, so see, this one, in the upper bound you can write like this way. Then they can be written like this way. And the margin of error, see, this one same as this one. It's nothing but the standard deviation of the estimate is called the standard error of the estimate. See? See? Then this one. So like that. So let's see, that's the major three, the major part in this whole discussion. We are doing. This is the part that there we are moving into that estimate. We did the point estimate. We did the point estimate. We want to do the testing. We want to do the confidence interval. But the point estimate is that estimate based on the sample. We have only one sample, okay? You don't have to worry about anything. We have only one sample. That's one sample would be enough for us to make the calculation. But in order to do the calculation, you have to have a framework already built up somewhere, because you are working on the built up framework. Where's our framework? Said we don't know the framework. We have to have an idea about the framework. That's what we are learning this stuff. Okay. So we get an idea later on with the aid of that our program in Python or any statistical or mathematical program, you can get the things done easily because we are dealing with the huge, massive data. You don't have to get things done by hand, but you have to have a kind of like a rough idea what's going on over here. So this is the part. Now we have a point estimate. This is what we have observed. Pretty much I mentioned about that one the other time too, that now instead of going to this one, we're gonna think about that some kind of a variation. Look at this is the variation in our estimate. That's the part that they were talking about. You see, variation in my estimate. How they gonna vary? Why they're going to vary? Because up to now, we have built models based on data to help us understand the data generating process, which is the population. For example, we have taken a sample of data, computed the mean of that particular variable, let's say height, and use that mean as an unbiased estimate of the population mean. See, you made the inferences. Estimation has been utilized to make inferences over the population mean. See, we know these models are wrong. We know this because there's a variation left over from the model. See, on the other hand, when we use some kind of a models, this model, can you remember that based on these kind of models we used? But if you use the mean only to estimate about this mean model, can you remember empty model? You have three models: empty model, group model, regression model. Those models still wrong because we know this because there's a variation left over from the model. Variation that we cannot explain, unexplained the variation, unexplained error. We have to squeeze the error variation down as far as we can. We know that. That's why we're gonna go to then we're gonna pick something. We're gonna pick this any single value to explain that whole distribution, which has the minimum sum of squared error or minimum mean squared error. And we have a good sense of how much error variation there is. How? We can quantify using what? Sum of squared error, variation, standard deviation. Those are the quantifications. See? We have some kind of a gauge about that good sense about how the error variation would be. Error. We talk about that in large scale in three models. Some sample, the empty model, group model, regression model. Talk about that and get a sense of how much error there is around the model. See, around the model. We have those ideas. But these estimates are also affected by another kind of a variation. See? Sampling variation. See, because of the sampling, we have another variation. See? See? We know that there's a variation left over from the model. See? That's a different thing. There's another variation we can talk about due to the sampling. We made the best estimate of the population parameter we could based on our sample of data. But if just by random sampling, we had ended up with a different sample, our estimate of the mean would be different. That's what we are trying to say. Let's say you go ahead and pick up a sample. You're gonna design an experiment, and then you collect the data. Later on, let's say that you're gonna do this one in different. Rather than picking from that particular sample, you're going to pick a different sample. Okay. With the different sample, you're going to end up with a different result. That variation has to be addressed because that by variation due to the sampling, should be addressed. That's what we are planning to do over here. Look at it. You get the thumb lens. You go to the center. You have a kind of a legacy. Nice graphical representation. Those are called exploratory data analytics. See, this is exploratory. Exploratory means you're going to just utilize the graphics to explain that summary of the data. The other one is called the descriptive data analytics. You're going to utilize the numerical value like a mean, median, mode, those things to explain the summary of your data. The third one is the predictive data analytics. That's the prediction we're going to do. That's the key part. So these are everything going to connect at the end of the day. Exploratory data analytics, descriptive data analytics, predictive data analytics. Predictive data analytics cannot be done standalone because you really need the aid of this EDA, exploratory data analytics, as well as descriptive data analytics, EDA. So that one, see, variation in individual score around the mean is something we can see by making histogram. See, variation of individual score around the mean can be visualized or explained exploratory, using exploratory data analytics, so that the descriptive analytics, we can do both ways. You can just draw the graph and talk about it, and then talk about that mathematical formula, and then talk about it, both ways. Okay. But variation in an estimate from the sample to sample is something we generally cannot see at all. This is from one sample. This whole thing for one sample. You pick a sample, you see that how your data, that let's say the heights or thumb lengths, been varying, okay, see how they varying around this one, see, around the average of this data. On the other hand, now you might be thinking why we picked that average. You know that when you have this kind of like a graph, what would be the best? These are called the distribution. This is a sample distribution, sample histogram. The best single number or value to explain this one would be the mean. We had that broader discussion. Why we not going to pick the median? We did that discussion too. So then we were working on that. And then we can see how our data being spread out around this one. That's a single value. Single. Okay, see? Individual score only. See? But we don't have any kind of like a discussion for how this means gonna vary now. That's where I'm targeting right now. I'm gonna say that, okay, based on this particular sample, you calculated this mean. Okay, how about that you pick a different sample? Would that produce the same sample mean? No. There's a high probability they're gonna differ from each other. If you keep doing this one for many times, there would be a variation in, I'm not talking about this data as well too, different histogram too. Since rather than talking about the histogram, it's easy for me to talk about its mean. The single value will pretty much take care of the whole thing, whole histogram, whole distribution. So let's talk about its center, which is the mean. The mean is gonna change from sample to sample. Once they change, there's a variation. Then we're gonna go ahead and draw the histogram for the means. That distribution we refer to as the sampling distribution. This one called the sample distribution. Based on a sample, one sample. Do you have any idea about the population distribution by looking at the shape of this one? Sometimes if it is by this one, we cannot. But if you increase the sample size, systematically, if you keep increasing, this will systematically become like a population distribution. So, but anyhow, we cannot do anything like that, because we in data analytics, we have only the data already being provided to us. We cannot do nothing, but we have to look into our the kind of a models, mathematical aspects, how they were working and their frameworks, everything. We have to have a clear idea. That's the framework, because by looking at this one, can I make a conclusion about the population from which this data has been taken out? No, sometimes no. We cannot. See, cannot say anything about this. See, by just this is all we have. That's called the sample histogram, sample distribution. Can I draw a smooth curve scheme in top of this one? Yeah, you can draw. Can I draw like a normal curve instead of working with this like a very weird shapes histogram? Can I work with a smooth, normally distributed curve? Yes, I can. We know how to do that one. Using GFDist, you can simply overlay a nice smooth curve on that one. We can take out that smooth curve and working on that one. I'm working on the sample. First type population distribution. Second type sample distribution. Now we're not happy about this one. We cannot be happy with only the 60. Can you remember when it comes to the confidence interval? I'm not happy with only one y bar. I need a whole range of y bars. This 60 is not enough. I need a lower bound and the whole averages going from the lower bound to all the way to the upper bound. I need all these averages to be taken into account. From that one, you can say that your average, observed average, would be included within that given interval. That's the kind of a discussion we try to build up. See, I need an interval. I don't need only that one y bar, which is, let's say in our example, 60. No, that's not enough. 60 or 59. I say that's not enough. I need a whole bunch. In order to get the whole bunches of this one, what we're gonna do with the aid of the given data, I'm gonna simulate data and build up some kind of a framework or some kind of a model with which that we can work on with the aid of our given data. That's what we are planning to do. So this 60, not enough. Then what are you gonna do? I'm gonna utilize the same technique to get the data. Let's say this is what I'm talking about. This is what I'm heading towards. Okay. At the end of the day, I'm gonna summarize everything together. Okay. So look at this one. So I have a population. See, I don't know population shapes. I'm not worried about the exploratory data analytics now. I'm interested in the descriptive data analytics. Okay. So that's why I'm focusing on that, the mathematical formula. Okay. See, let's say you're going to pick a sample. This is the population. Okay. This is the population. This is the population. Okay. You can pick with or without replacement. You can sampling, see, sampling. Okay. With or without replacement can be done. That's a one thing. Sampling. What kind of a sampling technique you're going to utilize in order to pick the sample? That's a different discussion. So like I say, sampling techniques, few of them I can list over here. Sampling technique. I can say random sampling. Random sampling. Or simple random sampling. They're not the same. Stratified sampling. Stratified sampling. See? Cluster sampling. See? Quota sampling. Like that. Okay. I'm just few of the sampling techniques. And you can do this one with or without replacement. I'm going to have population mean, which is denoted by mu, unknown. Population standard deviation, which is denoted by sigma. See, sigma, this one mu. I pick a one sample. So I'm going to pick sample one of size, let's say of size n equals 157. I think I'm relating to this one. Okay, this example here. I'm relating to this example. Fingers data 157. Let's see, where is that one? It's not there yet. Okay, I can't do this one too, but yeah, this one, I think. Yeah, see, recall we collected a sample in some length of undergraduate student. Just to overview, look at the histogram of sample distribution. This is real. This is real, not simulated. This is real. This is real. You know that. It's based on our data. Now, what we're gonna do, we are trying to simulate now. I'm in the simulation process. See? In 157, you calculate your sample mean. I would say that one y bar 1. See, I'm gonna pick another one. Sample. See, sample 2 of size n equals 157. I'm gonna calculate a sample mean. So y bar 2. They're both not the same. Let's say first one is 59. Second one maybe 60 or 60.2 like that. Okay. Okay. Then somewhere over here, you have the observed sample. See, observed sample, I'm gonna see, you have a observed sample. So as a sample we have with our hand, observed sample of size 157. See, Y bar, I would say this one observed. Oh, see, obs. I'm gonna put obs. That this one we have in our hand. See, we keep going. See? I'm gonna say sample 999th sample of size, let's say n equals 157. Then I'm gonna calculate Y bar 999. I'm not gonna pick these many samples. I'm not gonna pick. I have only one sample. I'm working with their sample. It's tedious process. Who has the time to go and then pick up that 1,000 sample? No, we don't do. We simulation process. This is we are trying to build up some abstract or theoretical model on which that you can work on. Then you can utilize this data to do all the calculations. That's what we are trying to build up. We assuming that if someone else has done, there are, let's say, 1,000 people have done this one differently, but with the same sample size. They pick they're going to go to the same population, pick the sample, using with or without replacement, doesn't matter. And sampling techniques, everybody's using the same technique. Let's say everybody's decided to go, we're going to go ahead and do the with replacement, yes. And then everybody decided to go with the stratified sampling technique. With that one in the setup ahead of the time, and later on they're going to pick the same number of sample the subjects from the same population. But when they calculate this one, or you can do by yourself thousands times. Doesn't matter. Doesn't matter. See? See? So the means not gonna be the same. That's all that I have to emphasize here. See, size n equals 157. See? Y bar 1,000. See. Now, if you look at these ones are not constant. They are varying. Y bars are varying. They are varying. See, Y bars are varying. See. Then on the other hand, Y bar, obs, we have with us that value, we know that one. It is what? 60.1. We know that one. That's different one. Other values we don't have with our hand, but we can simulate. It's all can be simulated, but these are varying, including this one, they are varying from each other. See? See? Therefore, Y bar can be graphically represented by a histogram. That's what we call the exploratory data analytics, EDA. Analytics. Okay. For that one, you can draw a histogram. See? Let's draw the histogram for that guy. Y bars, not for Y, okay? Not for thumb length. See? Y bar is nothing but average thumb length. Average thumb. See? Average thumb. See? Here you have the frequency. Or F or count. Hmm? So if you draw, let's say that your histogram is something like this. See? Y bar. Then I can draw like a smooth curve scheme in the top of this one. See? Then I go to the center. I'm going to go to the center. Center. I'm going to denote what? Mu y bar. See? Center. Mu y bar. See? That's the what? Mean of this particular histogram. We're going to call this one sampling histogram. That is based on sample histogram. Because of that, I'm going to call the distribution sampling distribution. Of whose sampling distribution? Y bar. It's not the sample distribution of Y. It's not the sample distribution of thumb length. It's the average thumb length we taken out. And based on that one, we built up this one. This is the mean of the sampling distribution of Y bar. Then this is, look at what we're gonna do, okay? This is nothing but, they think this is nothing but population mean. Look at what I wrote, population mean, population mean of thumb length, okay? Same thing, population mean. Population mean of the sampling distribution of Y bar is same as the population mean. Now, since the population mean is not available, I'm gonna replace population mean with its hat. Since mu is unknown, we can replace that. Mu hat is nothing but Y bar. Now again, we have a situation. We draw the histogram for Y bar. It's a Y bar. See, this is a particular that Y bar. At the center Y bar. Center Y bar is nothing but, where is the center Y bar? Y bar. Y bar is, can be replaced by what? There's a sample mean, see? It's nothing but sample mean. Sample mean. This is estimate of population mean. This can be replaced by Y bar obs. Observed sample mean. That is nothing but 60.1. That's how we got the center. So the bottom line, I'm sorry, 60.1 in this case. See, mu Y bar is 60.1. See, 60.1. In a similar fashion, I have to talk about its spread. Two things I have to talk about every time I draw the histogram. See, the spread. See, the spread. See, spread. I'm gonna say standard deviation of Y bar. See, sigma Y bar. Sigma Y bar. Okay, so that means I can go to the spread. See? Spread is denoted by sigma of Y bar. See, that's the nothing but standard deviation of the sampling distribution of Y bar. This one I can replace by sigma over square root n. Nothing but population standard deviation over square root sample size. Since you have a, see, you don't have a population one, I'm going to go to the head over square root, which means you go to the estimate of population standard deviation over sample size with square root n. I'm going to write same like that. And sigma hat, I can replace with the sample standard deviation. See? Sample standard deviation of y, okay? Divided by square root 10. See? Now it can be replaced by, see? S naught, see? Observed, see? Oh, observed. Observed standard deviation over this one. Observed sample standard deviation over square root 10. See, that value is observed sample standard deviation. You can normally get 8.73 over square root 157, which is 0.6967. So if you need this guy of that guy, this guy spread, this, if I use this value, there's nothing wrong with that one because of these or the rationale or that explanation or reasoning. I'm giving the reason. You cannot, you might be thinking why we are using this one because of this reason, this to this to that, that to that. So therefore, our sigma y bar, which is the standard deviation of the sampling distribution, is 0.6967. Another way I can call this one standard error. Standard error SE of y bar is 0.6967. It's the same thing. Standard error. Standard deviation of sampling distribution of y bar is same as the standard error of y bar. Y bar, now you might be thinking y bar is only like a fixed value. Why? You know that this discussion, it's not based on what we have. It's based on that already built up this simulated data. See, we had this one in the beginning. We work with that one. That's very beautiful, easy. Now we are we are exposed into like a little bit heavier stuff. Okay, but doesn't matter. You say, can we simulate all this? Can I draw this one? Yes, that's what we're gonna learn. Can I draw this one? Yes, using R, yes, we can do all of these. We can do. We can do. That's what we are planning to do. See? So to make this one little bit solidified, this way, I would go back to this one, distributions, again a little bit, and then we can move on to the data. We'll write the codes for this one, okay? We have three distributions. Population distribution. Whose population distribution? Of y. Y means thumb length. See how it looks like? It should be something like this. That bars are very thin and they were tightly stacked, and they keep going like this, like that. Then you have y on this axis and frequency, which is f on this axis. It's for a population. See, I can say for a population. And the second one for what? Sample distribution. Sample distribution of y. How it looks like? Sometimes we don't have a very nice one. Like see, this way. Sorry. We attach, then space. Sometimes go like this, go like this. See? Sample one. Not, we don't have like a very nice smooth curve or something. Can we get a smooth curve on top there? Yeah, that's a different story. This is F, this is still Y, this is for A sample. Third type, we're going to call that one sampling distribution. Distribution of not Y this time, Y bar. Sampling distribution of the mean of thumb length. How it looks like. It is kind of like a Y bar here. Its frequency here. It's also a little bit stacked like this. See? Not like a sample distribution. See? For many samples, this one has been drawn for many samples. Many simulated samples. Another way. Simulated or generated. Okay. Let's go to this mean. I'm going to write the mean of population. Mean of population, mu. Standard deviation, sigma. We have no clue about them. Unknown. 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 Let's go to the sample. Do you know the mean? Yes. Mean is Y bar. Y bar is 60.1. Y bar obs, okay? I would say Y bar obs. Do you know the standard deviation? S obs, which is 8.73. Can you get this way? Yes, by running that favorite stat or calculating. We have so many ways to get these values. How about the mean of this one? Mean of this one is nothing but mu Y bar. Mu of Y bar, which is replaced by Y bar obs, which is 60.1. That's one part. The second part, standard deviation is sigma of Y bar. Can you replace that one with S obs over square root 10? Yes, which is 0.6967. See? Then we can, here we can say Y bar obs is a Y bar obs is a point estimate of mean. Then S obs is a point estimate of sigma. It's another thing that you can mention too. Point estimate. How do you get this value in R? You can easily get this in R, no? You go to thumbstat, no? You go to thumb. Stat, if you build up thumb stats, favorite stat, favorite stats. You go to thumb, tilde, thumb, data, fingers, fingers. Then how do you get your Y bar obs? How do you get? You can get. You go to the mean, go to the thumb length and ask for the mean. Please give me the mean from thumbstat. Thumbstat like that data frame now. That's how you get the 60.1. Or what's the other way you can do? Or you can go straight to mean of go to fingers and go to what? Thumb. See, that's another way. 60.1. Oh, then you go to this one, S obs. How do you get S obs? You can go either in two ways, no? Go to the standard deviation of thumbstat, which is 8.73, see? Or you can go to standard deviation of the go to fingers data and then go to thumb and get the standard deviation. 8973. Either way. See, that's how we got that now. We utilize that one to on our framework, on our model. See, we have a see, look at distributions. They both look the same. That's what we are coming into the central limit theorem and try to connect these two. Connect these two by passing sample. The major part is this guy. In our whole discussion from now on, the sample is not playing any role. This guy is playing a role. Everything based on sampling distribution, everything based on the distribution of estimate. This is the nothing but the distribution of my estimate, point estimate. See? I was interested in the sample mean, the distribution of sample mean. See? So these are the ones that we are heavily utilized. That's what we are using pretty much all the time from now on. Forget about this one. We bypass and go. See? Those are the ones that we utilize over there. So when it comes to here, look at that. We were talking about very nice thing over here. These different kind of a distribution, how they built up. See, here these are thermostat token. Sample from one data, get a generation. Okay, we're gonna come to this one. Okay. How could let's look at this example? Okay. Hold on. We can do here too. Okay, let's go with this now first. Okay. I'm gonna go to this one, the previous one. Okay. Here, I'm gonna go with this one first. This one. The first one we talk about the variation under this one, the concept variation estimation. Now we know that was that estimation. Why is that? Let's look at an example, another example. See, to explore the concept of variation in estimate, let's go back to an example we explored on chapter 3, the throwing of a die. We start there because we know the DGT, and because we know what it is, we can investigate the variation across the samples using simulation techniques. This is one of the best examples. Okay, that's why, excuse me, they are citing that one, in which you have an idea about the population distribution. Normally we have no clue about the population distribution. In thumbnails, we have no clue about the population distribution. But when you throw a die, in that particular example, you have a clear idea about what the population distribution look like, how the sample distribution look like, how the sampling distribution look like. That's why they have selected that particular example, for you to convince that they show that one. Not in every example, no. Most of the scenarios, we have no clue about the population. We have no clue about the population, the distribution, population histogram. We have no clue. But this would be one of the best example in which we can talk about all these three. That's why they have chosen. We know, and we confirmed earlier, that in the long run of a population of die rolls has a uniform distribution. If we roll die one time, we don't know if it will come out 1, 2, 3, 4, 5, or 6. But if you throw that one die 10,000 times, or throw this die all the same time, 10,000 dice at the same time, or one die we roll in the 10,000 times, they would produce the same result. We should end up with a uniform distribution. Not that we just pick 10,000 as a really big number, but it could have been any big number, any number, okay, any number, okay, any larger number. How could you gonna do that one? See, look at, you built up a giant sample. Look at the resample technique. Resample means with replacement or without replacement. See? With replacement or without. With replacement. Otherwise, you cannot get this done after the 6th month because you want to do this one how many times? 10,000 times. When you do 10,000 times after the 6th entry, if you're not going to put it back without replacement, you cannot move forward. Okay. See, you use the resample. Resample 1 to 6, and then 10,000 times. If you do this one, that will show you, see, that one. But if you're gonna make that one like a with the like a very lower number, then it is for the sample. See, this is for the sample. This is for the population. See, that's why we call that one giant sample. See, giant sample is nothing but a population, or you can call the population. See, this is regular sample. And then later on, see, sample estimate, see, 24. Right? This will print the 24 numbers in sample. Then there you get the mean value. Okay. Let's from the sample to point. Okay, let's generate this one. Let's get this one. Let's see what they have to do here. Write code to simulate a random sample of 24 die. Okay, let's go to this one. Sample 1 to 6. Okay. (24) die rolls. This will print 24 numbers in sample, very random numbers. Then you're going to find the mean. See, 3.125. See, these are the numbers. On the first roll, we got 6. Second roll, we got 2, 3, 4, 1. Or on the other hand, if you're going to throw all the dice at the same time, 24 dice, and then have a look at it and see which one has rolled up, which number you're going to see on that top face, that number would be 6, 2, 3, 4 all the way up to this. See, like that. You're not going to get the same number here because it's a random. Okay, if you do another one, you get a different one. See, keep changing. It's average. It's average. See, different numbers. Okay, this variation. See, different. You see, if you do keep doing this one, it's going to change. That's what that change has to be addressed. That's what we are trying to do. That's why we are trying to get the mean value and try to draw a histogram for that one. See, can I draw a histogram for the mean value? Yes. That's called the sampling distribution. Can I draw like a histogram for one of these? Yes. That's called sample distribution. Can I draw a histogram for that whole population? Yes. By doing what? By increasing this guy. So we can get all three distribution done with this particular, very unique, this example. See, our sample in 24 and mean of this one. In your data camp, you might have gotten a different sample mean because your random sample is different from ours. If this were our only sample, we would use 3.875 as our best estimate of the population. But because we know that what the GDP looks like, we can know in this case what the mean of the population should be. See, population, can you get the population mean as well? Yes. That's why we are trying to do Hawaii. Now we go to the giant sample. Giant sample. See, 10,000. Mean of that one. I don't know how to, I don't want to see this, all the 10,000 over here to get messed up, but see, 3.5 on average. As a population, I'm going to increase this one. Let's see. I hope that we're not going to get stuck. See, almost 3.5. Is that true? Would that be 3.5? Would that be theoretically 3.5? If you roll a die What is the expectation of expectation? We call in the population average. Mu, do you know the mu? Yes, in this case, that's the interesting part. Mu is 3.5. Is that true? How could we know that? We can get this done in several ways. Several ways. You can remember. You can get this done in several ways. But this one and the ones that we saw over here. Okay, then let's say that we run this one again. Okay. Oh, no, I'm sorry. I'm the wrong place. Okay, restart session. Okay, 3.5. See? Okay, if you keep going this one, if you keep even at this stage, you see that they differ. They differ. Still not settled down. See, still not settled down to one value. Still not settled down to one value. In order for that to get into one, settle down with the one value, what are you supposed to do? You have to keep increasing this one, infinitely large sample size. When you make this one extremely large, that would come and then settle down to its theoretical value. This is called the empirical. Still, see, still keep going, see, changing. But it's trying to settle down to 3.5, trying to settle down to 3.5. But here, not the case. Here they differ, see, largely differ. Sometimes 3.3, sometimes 3.9, sometimes 3.7, 3.7, because we are using few number of dice, see, or rolls. See, here not like that. They are trying to settle down. We're going to show that one, what's going to happen in the central limit theorem at the end of the day. See, it's trying to settle down. See. So this, what's really going to happen over here is we can find the population. We can consider this one as a population. Sorry, I can keep increasing that one, but this is more than enough to get a rough idea. Even though there's a kind of like a variation that among all these numbers, let's say that this is 3.5, okay, for our convenience, because I don't know, increase this one and then sometimes get stuck. Okay, if you're going to do this 1 billion, trillion times or infinity many times, eventually it will settle down. Eventually settle down. See, eventually settle down. But I'm trying to say this one. See, you have, see, see, theoretical, that theoretical mu, see, mu. Do we know mu? See, you have y bar. Sample means this is n, number of dice, or see, number of dice, or number of rolls. That means like if you're going to roll some that one die, you can roll 1,000 times, so 1,000 dice you can roll one time, will produce the same result. See? At the primary state, when you have a 24, there means something. You keep adding, see, 1,000. Then you go to 10 to the, let's say 5, 10 to the 9, and then keep going, see, 10 to the 18, like that, see. What's going to happen? This value, okay, this value gonna, see, fluctuate. See, they will fluctuate. Yeah, up and down. Okay. See. Go from this side sometimes start. See. And then see. That's what's gonna happen. See. If you say, let's say that this one is, I'm gonna write this one, mu, population mean. Okay, this one population mean, population average is 3.5. I can write this one in another way. Expected value of y. See, EY. Other way of writing. See? Or some people, they prefer to write like a mu of y. See? More specifically. Doesn't matter. Okay. This value is we call the, when you roll a die, what's the average? How do you get the average? We're going to come to that on theoretical or abstract, okay, or classical, expected value of the number is 3.5. You might gonna get 3.5 on expectation, see? Expected average value. But see, you have a here sample average. This is what they say. They say that when you increase the sample size, when you keep going and increase the sample size, your sample average come and settle down with the theoretical value. This one we call the empirical or experimental. See, experimental. See, experimental average. See, empirical average. So they think you see your y bar come and settle down to mu when you increase. I'm gonna say to increase n. See, this is what called the law of large numbers. Law of large numbers, LLM. That's what they were talking about. See? At the end of the day, how could we got the theoretical value? That's another discussion. Sample, for the sample, you can get the value every time you do this one. See, because sometimes at a certain point you feel like this is also a sample, even though it's a giant sample, it's like a sample. See, it's not settled down yet, it's a halfway through, but these are drastically different from each other. See, sometimes it's above the average, above that population average, or below, doesn't matter. You have to take into account both sides. That is like in a shock absorber. See, so or if you're gonna drop like that rubber ball, it's gonna see keep going up and down and then go and settle down at the end of the day, then losing energy. That's the same concept. Same concept. Most of that the concept in physics being incorporated into these statistics, because that's why we call about the moments about the standard deviation, mean like that. Okay, see, when 24 is somewhere here, they're not the same. Let's say the value is like a 3.5. Let's say this value is 3.8. So let's say that you got like a 3.8 value at a certain, see, 3.8. See, your y bar is 3.8. See, like that. Sometime it might be that below that one, maybe 3.2, doesn't matter. It happens. So you have to make sure that you're going to take into account all the that numbers that you can think of. That's why we're going to draw like this way. But at the end of the day, when you increase the sample, see, increase the sample size or that number of that dice or the number of rows, eventually you're going to get the same value. Expectation for that one, for rolling a die with the expectation would in a long run, what would be the number that you're going to get? 3.5. See, in a long run, see, on a long run, you want to find the the profit, expected profit. In a long run, you want to find whether there are any losses, revenue, so many things that you taken into account going through this route. Okay, but here that the other important thing, how do you know this 3.5? Where the 3.5 come from? Let's have a look at it, this one, 3.5 thing. Okay, what I'm gonna do, I'm gonna go back to this one. See? Type of distribution, you know, there are three types. This is the best example in which that we can talk about all three. So first one is population distribution. See, population distribution. See, look at the population distribution. See, I'm going to go ahead and look at an experiment example. I would say probabilistic or random. That's called the random experiment. Okay, experiment. I'm going to use this abbreviation expt dot. Is nothing but roll in a die. Roll in a die. Let's say 10 to the 6 times, million times. Okay. Or roll in 10 to the 6 dice one time. These all are very hypothetical. Okay. We're not going to do this one for practically. Okay. But the theory will be based on this kind of that structure. Once you do that one, they say when you draw the histogram, see, when you draw the histogram, see, what do you get? See, you have a 1 here, 2 here, 3 here, 4 here, 5 here, 6 here. See? You have a this one. I'm going to call this one giant sample because that's the name that they have given here. How did you get the giant sample? In R, giant sample, you get by resampling, resample 1 to 6 numbers 10 to the 6 times. See, and then you can call this one population by putting this one into a data frame. Okay, I'm going to put this into a data frame. Data frame into a giant sample. This data frame. Then you can draw the histogram. Okay, then you can draw the histogram. How do you draw the histogram? GF histogram. You go to your variable. Variable is nothing but giant sample. Okay. And data is nothing but population. Its name is population. You have to do one more thing. You have to make sure you pick the bins. Otherwise, they will be separated like a bar graph. 6. Okay, make sure to get them attached to each other. So in this size, you have a what? Let's say you have a relative frequency. Okay, I'm going to say relative frequency is nothing but relative frequency. I would say rel frequency for abbreviation. As a notation, I put RS. It is nothing but frequency over n. Okay? Frequency over n. If you get this one, you know that each one going to have a chance of getting this each number with what? 1/6. See, 1/6 would be relative frequency. See, so you're going to have this one. They were attached to each other. You know, see this one 5 point, and it's going to go to see. This one is 6.5. See, the end of the day. See. So eventually, if you have, see, this is for the 1, this is for 2, 3, 4, 5, 6, 7. That's a uniform distribution. This one, it's called the uniform. See, look at the shape. If you draw any smooth curve scheme in the top of that one, you're going to have a straight line parallel to the x-axis. Giant sample. See, uniform distribution. And more specifically, I can say discrete uniform. Discretize. Okay, because the numbers 1, 2, 3 like that. There's no guessing. See? Now you really need to find the mean. That's the one that I really want to find the mean of this guy because I have already drawn the population distribution. I want to find the mean. See, how do you find it? Let's go to method 1. See, you're going to find the mean of giant sample. See, you can find the mean, go to giant sample. See. Or in another way, it's same as mean, go to mean, invoke mean on population, and then go to giant sample. That's another way that will produce you 3 point, let's say that's 0, 0, like this. And you run, see, because that is still not to the infinitely large, it's 10 to the 6. Look at the method 2. Another way to get this number. I'm going to approximate with this one, say 3.5. See? 3.5. The other one, look at. I'm going to, with the aid of the uniform distribution properties, this is y, this is the frequency. Let's say that this is the starting point. I'm going to say a equals 1, the last number, b equals 6. Okay. And that's the uniform distribution. From the uniform distribution, I go to the center. See, I go to the center. How do you find the center of a uniform distribution? Median. Median and mean gonna fall at the same place since you have the same frequencies. See, same frequency for each one. There's no mode. No mode, okay? No mode. But how do you get the same frequency? What's it gonna do? You're gonna add a plus b and divide by 2. See, 1 plus 6 divided by 2, 1 divided by 2, 3.5. See, that's another way to get the answer. See, that's another way to get the answer. With the aid of the uniform distribution properties. Uniform distributions average will be calculated by adding the endpoints. A equals 1 and 6. So, and then divide by 2. Get the center. What's the other way to get this one? I'm on the population. Okay, I'm still on the population. What's the third method? See? So this the same thing that if you use the R, in R you can say uniform. See, I'm using the uniform bounds. Uniform bounds only. See, with the aid of uniform bounds, C1, 6. How do you find the? You're gonna build up C1 and 6 only, and you're gonna say the mean of the uniform bounds. See, mean of uniform bounds. Uniform. I'm sorry, uniform bounds. I would say bounds. See? That would give you the 3.5. Not. Then let's go to the method 3. Method 3. How do you find the mean? Very easy. Mean, you're going to add all the numbers. 1, you have 1, you have a 2, you have a 3, you have a 4, you have a 5, you have a 6, and divide by 6. See? That would give you what? 21 over 6, which is 3.5. See? Another way to do that. You're going to add the numbers. Which numbers on that this die? 1, 3, 6, 10, 15, 21 over 6. So I'm going to do this one, another something to this one. I'm going to split this one like this. Look at what I'm going to do. 1 plus 2 plus 3 plus 4 plus 5 plus 6. I'm going to take the 1/6 out. Then I'm going to rewrite this one. 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. It's like what? 1/6 is nothing but the probability. See, probability of getting y. See, this is 1/6. It's nothing but relative frequency is nothing but probability of y. Probability of getting any number. See, probability of getting any number. So this is nothing but look like you have a y times the probability of y and sum them up. See, that's another way to find the mean. How do you find the mean? Expected value or mu. See, with this formula. the formula has been utilized. So you go to some reading, its corresponding probability plus go to second reading probability plus. See? I'm talking about mu over here, okay? We had that discussion in the beginning. I'm talking about mu. This whole discussion because we are on population, mean population mean. See, this mean. Or they use this one to expected value of y, expectation of y. That's the same thing. That's the same thing. See, so they were nicely structured because at the end of the day, we don't add like this. This is the way how we do things. We're gonna go and see the profit, expected profit. If you want, you go and say the sales, and with the what is the probability of selling that one percentage, then multiply all the time. Everything being incorporated with this randomness. Random should be taken into account. See? You have this value sales. Sales just you cannot say simply sales only. See, what's the probability of selling that kind of the merchandise? What is the chance of selling that one? What's the likelihood of selling that one for a given period of time? Or if you're going to incorporate the time factor, it's getting very nasty. I mean, like a stochastic setting you have to utilize. So to that, what we are trying to do at this primary stage, you learn something. Later on, you're going to add on top of that one, you instead of using this any formula or anything or any distribution, you are trying to use the machine learning. But the machine learning has to be utilized for the data. But if data appears in a nasty way, you have to be very careful. They come in so many forms. So many forms data. So that's why you have to have a kind of a rigorous, in-depth that understanding what's going on. Otherwise, some stuff you get stuck, cannot tackle. See? Okay. So these are the three ways that you got the 3.5. I'm talking about this one, we got that one. This is also 3.5. Okay. You get that one. We built up a certain 3.5. See? And this one 3.5. In R, if you use the R, that's another way to look this one. You can say the die outcomes. You can get the die outcomes, see 1, 2, 3, 4, 5, and 6, and then find the mean. See? Mean of die outcomes. See? See? That could give you 3.5. See? If you don't want to do by hand, then you can use the programming all the time. Either way, see? It's fine. See? Anyway, that you have to get the idea of what's going on over here. That's the most important thing. 3.5. See? 3.5 with the aid of the uniform distribution property you utilize and get that one. Our experiment would be roll in a die. Roll in a die, but see? See? So that means some length are what? This here at the end of the day, you can infer some lengths are for this one. Okay, I'm gonna show you another one. Look at, I'm gonna say thumb. See? In this setting, this is how we're gonna write. Thumb means y. I would use in this one tilde. See? Tilde means what? Is distributed. I mean, population setting. Uniformly, you with the endpoint 1 and 6. See? Uniform distribution. This means uniform distribution. Uniform. U stand for uniform distribution. And in the population setting, you can say like that. That means you can say thumb lengths are. Okay? Thumb length uniformly. I'm sorry, I'm not thumbnail, the die. The thumbnail, I'm sorry. It's not thumbnail. The, I'm gonna go back to this one. Not, see, sorry. Not the thumbnail, this die number, see, number on die, I'm sorry, number on die, uniform, numbers, die, not this one, not this one, not this one, uniformly distributed, and was distributed with this abbreviation like uniformly distributed. So that one. So that if you go to the second one, you saw that the sample distribution. Look at the sample distribution. Sample distribution. Again, I'm gonna say my as an example, probabilistic or random experiment would be what? Roll a die, see, 24 times. See, roll a die 24 times. So again, if you draw histogram for this one, see, so 1, 2, 3, 4, 5, and 6. They're not going to look like a sample that same distribution that we saw earlier, uniform distribution. No, they differ. See, sometimes see like this. See? This is right. If that's some length, this let's say that relative frequency, RF, relative frequency. Frequency over n. See? This one we can say small sample. See, or that the other one giant sample in R. How do you get this one in R? Small sample, same thing. Sample, we go to resample. 1 to 6, 24. See? And then I would say this one is a sample. Okay, I'm going to put a data frame. Small sample. For this one also, for the histogram, you can, for the histogram, you can use the beams, okay? The histogram and the small sample, see? Small sample. And the data would be sample and beams, you see, 6. And again, for this one, if you go to the mean of this one, that's y bar. See, mean. If you go to the mean of this one, see, same way we were looking for the mean for that one. So can you remember that mean, giant sample under that one? I'm gonna come back to this one. See, that is nothing but mu. Okay, mu. See, mu you're looking for. See here, mu you're looking for. Median and the mean the same thing. See. In the both three methods, see, this one, see, that's a mu 2. So here we are looking for y bar. See, y bar obs actually. See, y bar obs would be what? You go to the mean of small samples. So mean of go to the population which is sample. Within sample, you go to the variable. Small sample. That would give you a certain value. See, certain value based on that you the way that you have run that. See, see, that's the y bar of same thing that you can for that one. Let's say based on that sample, based on that particular sample. See, based on that particular sample. See, one of these values. See, 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 one of these values. Okay. But in this case, I do some kind of adjustment here. Since you can observe everything, I simply call this one y bar as well. See, you can observe everything. See, you don't have to simulate it then. See, you can see same thing. See now, sorry, then now since you have simulated, now you see you can see that one. See. But you have a one sample. If you have done this one time, and the roll that one empirically, and that value you have keep with you, that's a different thing. 24 times and that those values is different. I'm just simulating everything. These are simulations. See, these are simulations. See, so it's very reasonable. If I'm gonna go ahead and take this out, I think, because since we don't have a observe, we're gonna utilize observe that term to something that based on the sample that we have in our hand. So I simply call this one y bar. Okay. So the same way that then what? Then you can think about that the standard deviation the same way. Let's see. Standard deviation. See, S. This is the standard deviation of small sample. Oh, same thing, standard deviation, go to the sample and then go to the small sample. That's a variable. Okay. And based on it's going to change from sample to sample. So sample to sample, it's going to change from sample to sample based on that one of spar type utilized to the based on whatever the sample that we have in our hand. Since we don't have such a thing, we keep like this. See, fiber. Now, since you have so many y bars, see, now you have so many y bars. See, how do you that create the so many the y bars? See, in R, you're gonna create now. The next one is the sample distribution, and then on the other hand, for this one, if I'm gonna ask you to write a y bar, see, y bar is nothing but see mu hat. Can I say mu hat? Yes. This one is nothing but sigma hat. See, can I say that one? Yes. See, sigma hat. See. Some people they write like this way, sigma of hat of y, which is s of y. See, like that. Can see like that. The same way here. The mean you can say mu of y. See, or mu hat of y. See, it's the same thing. With various notations. Notations. Okay. So then let's look at the third one, sampling distribution. Let's say that how to get the sampling distribution. Third one, sampling distribution. See, when you do sampling distribution, it becomes like a what? See, now I'm gonna get this done for that means. Okay, I'm gonna draw this one for means. Okay, see, I have a means here. Means y bar for mean. I'm gonna do this one for mean. And then relative frequency again. And then if you do this one, you're gonna see something like this. Very nice one. See, nice one. If you smooth curves, even that one looks like a normal curve. How do you get this done? How do you get this, generate that one? I'm talking about this picture. The picture here, this one. Something like this. You have a population. From the population, you're gonna pick the sample one at a time for this particular example, okay? This example for the thumb length, but this one like this, see? Whole bunch of these. Okay, that's what we are trying to generate. You're gonna pick like a sample, small sample, and then we calculate the mean value, and then we keep adding that one and keep that one, and with the aid of that one, we are trying to draw the histogram. Okay, that's what we are trying to do. Let's do that using R. Okay, so sampling distribution, I'm gonna get something called bunch of means. Okay, I'm gonna call that one bunch of means. How do you get the bunch of means? Look at how do I get? I'm gonna resample. See, resample. See, 1 to 6. See, 24. From that one, get the resample by through that resampling function. I'm gonna get a sample of the size 24. Sample of size 24. Then I'm gonna calculate its mean. How do you calculate? I'm gonna invoke this mean function. See, mean. See, mean. See, mean. Not mean. Okay. Then what? I'm gonna repeat this one. How many times? 1,000 times. Can you remember? We used to do this 1,000 times. Do 1,000. This one stop. 2,000 times. You get the one sample of size 24. Sample of size 24. See, this is what I'm trying to do. See, sample one of size 24. You go y bar 1. See, sample 1 n equals 24. See, then you go to the second one, y bar 2. Sample 2 n equals 24, still the same, dot dot dot. You go to the last one, sample 1,000. Size is what? Size is n equals 24, but you have repeated that 1,000 times, y bar 1,000. That's what we are trying to do. That's the code. See? See? So this is, in this situation, since you are using do, this is the data frame. It's a data frame by itself. That's the data frame. This is the variable. So you don't have to put into a data frame again. It's already done because of this. This one is a star, okay? This star. Do star mean resample. See? This one, this should be closed, okay? 2 times closed. This one. Why not coming? This one. So there's a punch over here. This one close. Yeah, close. See? Right there. Can you draw the histogram for this one? Yes. EF histogram. I'm going to draw this one for my variable, which is mean. Okay. And then what? I need the data. Data name is bunch of means. That's it. You don't need to use the beans, okay? You don't use the beans. You don't have to use the beans because now it's based on so many thousand entries you have. Based on that one, you build up a histogram. Now I need what? I need this guy. Mu of y bar. I need the mu of y bar. See, how do you find that one? I'm gonna go to the mean, bunch of means, and go inside mean. Bunch of means is my data frame, and go. Oh, I go to the mean of mean. Sorry, I cannot go to the data variable. Sorry. This the one bunch of means and means. See? But it has not been built up into data frame. Data frame is already there, bunch of means and means. See? That's the mean. See? So this mu is nothing but see, should be equals to what? Population mean. population mean. Population mean should equals to the population mean. Let's say that's the case. Okay, let's go ahead and see. Okay, let's keep going. 3.85. That's okay. Then giant sample mean, we got that one. Then outcome, we know that one. Okay. Sample 24 several, and now they come to this step. They come to that step by step, but you can use one shot here. See, 2-3 terms. Instead of that one, you can do this on 10 terms. Okay. Then you do this one 10 means. See? 10 means, okay. Bunch of means. See? See? I call the bunch of means 10 times. Okay. Then it's like this. When you do 10 times. If you do this one for 1,000 times, 1,000 times. Okay. Yeah. And then draw the histogram. See, mean, data bunch of, and then vertical line, blah, blah, blah. See, see, look at it. So that's it. It's the distribution of means or sampling distribution of means. So let's look at its mean. Okay, I want to look at whether they. I want to. Oh, sorry. Let's go ahead and here mean of bunch of means. Bunch of means, and then this. See, 3.5. It's same as the population mean. That's what I said. See? Same as the population mean, which is 3.5. That's the beauty of this. Approximately, okay? Approximately. Should be. See? See? Then you go to the standard deviation of y bar. What are you going to do? Standard deviation of bunch of means. And then go to mean. Going to find the standard deviation of mean. Same as sigma over square root n. Sigma is how much? Standard deviation of sample. Can you remember? Sample, sorry, standard deviation of population. We had that one. Let me see. I'm going to go back. The population distribution. Sample distribution. Population distribution. Did we calculate this? No, we didn't calculate. Can we calculate that one? Yes. I want a little bit calculate this one. We talk about all that finding that means only. I can calculate. Go back, go back, go back, back. Go to the giant sample. No, not this one. Giant sample. Yeah, here. Okay, giant sample 1.6. Can I find the mean? Okay, here. Random sample of 24. No, I'm gonna run anyway. I can do this one. Okay, giant sample. Let's go to this giant sample. Resample 1 to 6. Sorry, 1,000, 100,000. Not the 24. This one, then we turn 1,000. And for this one, copy and then giant sample. Can you remember this one? We call this one mean. Go to giant sample. or you can put into like a data frame. The population, I made it a population, okay, like that. Okay, I can say population data dot frame and sample. Calculate the mean. Okay, mean of this one, mean of the sample. You can go straight to that one. And standard deviation, see, mean of sample or mean of go to the population and then sample. That's so standard deviation of 1.7. Okay, 1.7. 1.7. Let's see, 1.7. Standard deviation 1.7. 1.7. Each one has a 24, no? 24. Each sample is 24 in this one, no? Sample size. Yeah, 24. Okay, let's, but rather than that one, we go to back to that one and then calculate again. Okay, I'm going to go to the bunch of means, that place. Bunch of means should be at the one. Bunch of means. Yeah, do this one for 24 times. Okay, not this one. This one, no. 1,000 times. 1,000 times. And then I really need mean of bunch of means. So go to bunch of means. This is the data frame, this is the mean, okay? That's a data frame already built in over there. So bunch of means and then go to mean and the standard deviation is okay. Let's see. Point 36. 36. 36. 33. Let me see. 1.7 square root. Sorry. 1.7. Okay, it's coming close to that one. So that when you calculate this one, 36, let's say 36, okay? 36, okay? This one you got from by running this one, you got that one 36, see? 0.36, okay? Let's say 0.36. Calculating this one, approximately you get 0.35, see? They're both the same. See, that's what I'm trying to say. It is same as this one. So you go in this route and get this one is same as you go and get in this route. That's the part we are emphasizing here mainly. When you divide that 1.7 divided by square root 24, I got 0.3470 approximately. That's 0.35. On this one, when you run this one, We've got 0.36 to keep to the 2 decimal places if you want to keep like that. See, because these are based on this random numbers. See, random numbers. That's what it says. So this is the particular example in which we can easily distinguish and talk about everything, because the population we know, sample we know, sampling distribution we know. Okay? That's a very good example. Okay? So I will write over here. They're talking about the mu. I'm talking about sigma. Sigma. Okay. Sigma. If sigma known, you can use the sigma. Okay. Since here sigma known, sigma is nothing but standard deviation of go to giant sample. The standard deviation of giant sample. Standard deviation of giant sample. Oh, standard deviation of population and then giant sample. Population and then sample. Population and giant sample. Sample. We found this one 1.7. 1.7. 1.7. It is still not exactly uniform because we haven't used the massively, infinitely large sample to make it a perfect population. But this approximation more than enough. 1.7. And you might be thinking, why we not going to replace this one with sample? Yeah, go to the sample and then let's think about that you are here and then try that way too. The sample distribution one. Okay, sample distribution. You go over here. You found see mean. See, like this way, this way, this way. Any value you can put it over here. We can calculate if you want. For based on one sample, one random sample. Okay. So let's go to this one here. See, bunch of no, not here. I'm sorry, not here. Not here. We can do this one. I'm talking about the sample. I'm talking about sample. Okay. I'm looking for the not this one. Sample. Simply with the 24. Resampling with the 24. That one. Here. Okay. Standing. Sandbox over here. Yes. This one, let's see that just a sample. Okay. Resample 124. See. Resample 124. I'm gonna say no. For that one, I'm gonna say small sample first. Small sample. Sample doesn't matter. Okay, sample would be data frame. Again, small sample. Go like this. And then let's find the mean of small sample. Okay, mean of small sample simply and standard deviation of small sample. Okay, this is this one. Okay, 1.8. See, very close. 1.8. Instead of that one, 1.8. That what I'm trying to say here is based on the sample. Can I replace this one? Okay, another way to look at it. I'm gonna replace S over square root 10. S is how much? 1.8. And the 24. So 1.8. 1.8 1.8. 1.8 divided by square root 24.36. 0.36. The same as the population one. See, so you can straight go and calculate. With the aid of population standard deviation, you can calculate. Since it's known, with the aid of sample, you can calculate. See, interesting. See? For the sample one, I would say, I'm going to put these values so you can say based on one sample, 3.0 and 1.8. 3.0 and 1.8. 3.0. 3.0 and this one 3.8 and this one is 1.8. 1.8 and 3.8. I'm sorry. So let me 3.0. 3.0 and 1.8. See, if you want, you can then for the sampling distribution, either you can use this guy or the population. With the population we had that one, you can use it. Okay. 1.8. See, if you go back to population, where I put the standard deviation. Here. 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 Okay. Like that. Okay. You see the shapes, almost bell shape. Would that be bell shape? Yes, that's what the central limit theorem. Is this a bell shape? Is this a bell shape? Population? No. Population uniform. Sample distribution. Like say different. Can I draw a smooth curve on scheme in the top of? Yes, you can. That's a different story. Would that be beneficial for doing something like this if you have something like that? Okay. See this one completely. See, gonna look like this one. That's what the central limit theorem is telling at the end of the day. See, central limit theorem say that one. Okay, we'll mention the central limit theorem and then we can stop. Okay, I'm gonna just mention that one. We can pick it up from there and stay. Just you see, let's a little bit talk about that one and then we can stop the central limit theorem. CLT is the backbone of statistics. This is the major guy. Okay. Now we are trying to connect two things as I did say earlier. I'm going to say population distribution here. I'm interested in the sampling distribution. That's it. At the primary stage, we are interested in mean. Okay. So let's say that for the population, somebody has done this one Y. It's bell shaped. See, bell shaped. Normally distributed. Normal. See, you can say, see, bell shaped. Distribution is bell shaped. Symmetry. Symmetry. Mean. Population mean is mu. Standard deviation is sigma. Then what? Then is the mean. This length is called the spread. See? This is mean. This is standard deviation is sigma. Bell-shaped population distribution. See, symmetric. We can say y is normally distributed with a mean of mu and standard deviation of sigma. That's how we're gonna say. How do you denote that one? Look at how I denote that one. Okay, y tilde n to normally put the mu first and sigma. That's the notation. When you write like that, that's more than enough. See, if you wanna know about that. Okay, they say that if the population distribution is this one, your sampling distribution of y bar is also normally distributed. See, 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 from here to here. What? Regardless of the sample size n. Whether it's large or small doesn't matter. If your population distribution is this bell-shaped or that normal, see normal, see, you can say normal distribution, see, and normal distribution, normal or Gaussian. That's been named after Carl Gauss. Is considered to be the father of mathematics. See? See? So like that, regardless of the size, if you bell-shaped, if you feel like that your population distribution is bell-shaped, your sampling distribution definitely bell-shaped. I don't have to write if this bell-shaped. Okay, I'm gonna write the properties here too for you to be bell-shaped. Okay, bell-shaped, symmetric. Okay, mean. How do you denote the mean? Mean you can remember mu of y bar. See, mu of y bar. Okay, it's same as mu. You can remember we found that one. And the spread standard deviation of the sampling distribution sigma of y bar, which is sigma over square root 10, or s over square root 10 if it's not available. We know that. But symmetric mean is nothing but mu of y bar, same as population mean. See? And standard deviation sigma of y bar, same as sigma over square root 10. See? And normal, which means Gaussian, the Gaussian distribution. You can say y bar is normally distributed. Normally distributed with a mean of mu y bar, which is mu, and a standard deviation of sigma y bar, which is sigma over square root 10. See? That's first property. That's one. Let's say that you have for the population, again, population, you have asymmetric, skewed one. Okay. You have a skewed one. See? I would say somewhere here mean, see? Mean is again mu. Standard deviation is sigma. See? Then what's going to happen? Based on that, this is a population distribution. Okay, population distribution is asymmetric. This is sampling distribution here. Based on the size. Size means what? When n is greater than or equals 30, or n is less than 30. See? It's a small sample. That's the cutoff value. It's a large sample. Practitioners think that when size is more than 30, it can be considered like a large sample. It's a large sample. Still, regardless of that the shape, if you are using large sample, so Y bar, see, bell shapes, see, symmetry. I don't have to write all the details over here. Now you know that mean is nothing but mu Y bar, which is mu. Standard deviation is sigma of Y bar, subscript Y bar, which is same as sigma over square root 10. And it is less than, but asymmetric. What are you going to do? You are using advanced statistical measures such as non-parametric procedure. Non-parametric procedure example, decision tree, machine learning. See, but in a situation like this, you don't need the distribution. You drop distribution. You say it's a headache to do work with the distribution. They go to another framework called the non-parametric setting. Most of the biomedical research are nowadays done using the non-parametric setting under that one. That's why decision tree also being utilized in the machine learning as a like an easy way to that tackle that regression. Regression model can be easy to tackle rather than using the heavy that mathematical models. But they still use, okay, it depends on it. That's the base. But still in that R part, the function we utilize to write draw the decision tree, but still you use the same format like in a regression format because that's the basis. Basis cannot be taken out. That's why you have to learn that one. So this is kind of like that. That's a central thing theorem says. You see? That's why in a pictorial form, I just represent rather than writing. Okay? If it is population is like this, your sampling distribution like that. If the population distribution is uniform, since we are using that 24 size 24 large sample. Or on the other hand, now we have two things that we should take into account here. Look at the way that we have over here, sample size and the repetition size. See, sample size 24. I'm sorry, there's a sample size repetition 24. Can we repetitions 1,000 times? See, can you remember at the end of the day on this one that when you when it comes to here, see, can you remember distinguishable that we can talk about these two a little bit? No. Hold on, three sample. Here, see, okay, 24 and 1,000. So now we have a kind of a lack of which one will produce the better result by increasing the sample size or increasing the repetition size. That's the discussion we have in homework. So I'm sorry that I forget to that. The first thing I wanna know that. Yeah. Here. So this one, let's go to content. Yeah. So you can see that assignment. Midterm is nothing but that chapter 9 review question. I want to check that whether they will. Assignment, let's go to this one, go to assignment. Yeah, week 2 assignments. You have seen If you don't have RMD file, you can just open like R file and work it and then copy and paste from the previous that data importing that R codes. Okay, but here we have RMD. First homework we didn't have, but you don't have to worry about it. Simulated data. This time we use the simulated data. What I'm trying to say that just 2 minutes. Okay, give me just 2 minutes and then I'm gonna stop. Okay. Okay, this is the simulated data. This is the homework. See, but the data, if you look at the data, look at the data real quick. And go to simulated data. Okay, data being simulated, thinking that download and import the sim data, sim_data.csv file, which contains 1,000 samples. Columns are samples of 100 students. Rows are the student per sample. Each sample was taken each month at NU for the past 1,000 months of student currently enrolled in a class for that month. Each cell is the age of a student for a term. For histogram, if you have an error message with the histogram, use hist and the AB line function to create histogram. These are simulated data. There's no way that somebody gonna collected this data for 1,000 months. Okay. So anyhow, see, these are like, see, this is a one sample. It's another sample, third sample, fourth sample. And how many students in each sample? Not 24 in this case, not 157 like in thumb example. Fingers example, 157. Die roll, we have only 24 rolls. Okay, 24 rolls. 24 rolls are done, that one, the samples, but been done 1,000 times. Here, 100 students, age being recorded for 1,000 times, 1,000 samples. Now the thing is that whether we're going to by increase in the sample size or by increasing the repetition size, which way that we can get the better result. We have that kind of a discussion we built in up here. Just at the end of the day, see. See, that at the end of the day, by increasing, look at what we are doing over here. Sorry. Our function apply, you can use apply. We're going to talk about more ways to get this done, and the one shot we can get this done. See, 100. See, mean with the 100 sample with 10 students. See, instead of 100 students, they try with the 10 students. Then next one, 100 sample with 1,000. See, I'm sorry, but instead get 100 sample, get 1,000 sample. Now get the 1,000 sample. Instead of this one, I'm going to increase the number of samples rather than number of students. Keep the same student. Now what? But instead of 10 students, now go to 1,000 students. That's right. We do two ways. Sometimes we can increase that sample size. Sometimes we can increase the number of repetitions. See? How many samples? Number of samples or sample size? Number of samples or sample size? Which one would produce the better result? I would prefer to use, okay, in the very beginning, sample size is denoted by simple length. Sample number is denoted by, I prefer to use M. This is what I'm talking about. I prefer to use M, M, okay. M for this one. See, sample M equals 1,000. See? So sample size 1,000. See? Number of samples 10,000. Each sample size I can denote by N, which is 157 in this particular example. That's the same idea. So my question is, by increasing N or M, you get the better results. We already discussed that by increasing N, but practically you can see from this exam homework how that can be done from different kind of a variations. We do different, sometimes we're gonna increase the sample, sometimes we're gonna increase the sample size, and then we can do the discussion. Okay, we can continue this discussion on, we have plenty of time Thursday, sorry, Wednesday and Thursday. Do you guys have any questions? If not, I'm gonna let you go. Okay, you guys have a happy Halloween, and then good night and stay safe and be well, and then see you guys on Wednesday. Okay, take care. Thank you very much. Okay, thank you very much. Thank you. Bye. Thank you. Have a good night. Take care. Thank you very much. Thank you very much. Yeah, thank you. Thank you. Good night. Thank you. Good night. Take care. Bye.